Hi everyone. So some time ago I made a video where I evaluated the integral that we see here, which is the integral from 0 to a of sine to the power of m of n pi over a times x with respect to x, where m and n are natural numbers. Okay, and I did that using a reduction formula. What I'm going to do in this video is evaluate the same integral but via a completely different method. And there's going to be one slight difference, which is we are only going to look at the case where m is even. Okay, so it turns out that the case where m is odd is much more difficult. I'm still working on that. So for now, we're just going to say that m is an even integer. Okay, and the basis of the method which I want to go over today is that we can define the sine function of some parameter theta in a way that involves complex numbers. We can write it as e to the I theta minus e to the minus I theta divided by 2i. Okay, that follows from the fact that e to the I theta is cos theta plus I sine theta. Okay, so let's see what happens if we just plug in that definition of sine into our integral here. So we are going to get, well, because we're raising the whole thing to the power of m, we're going to have a constant term of 1 over 2i to the power of m, and because that's a constant, we can just write that in front of the integral, right? So we get a 1 over 2i to the power m, and then integral from 0 to a of, well, we're going to have two terms. We're going to have e to the I n pi over a x, and then we're going to have minus e to the, well, the same thing but negative, right? Minus I n pi over a times x. This whole thing raised to the power of m and then integrated with respect to x. Okay, so far we've just used this definition of sine. Now, notice that we have a sum of two terms in brackets and the whole thing is raised to the power of m. So what can we do in that kind of scenario? We can do a binomial expansion, right? Especially because m is an integer, we can expand these brackets and get a series with a finite number of terms. So let's do that binomial expansion. We are still going to have this 1 over 2i to the m out the front, and then we're going to have this integral from 0 to a. Okay, so our binomial expansion is going to be a sum of terms, so let's use this sigma notation, and I'm going to index the terms by another variable k. That's going to run from 0 up to m. And remember, when you do a binomial expansion, you have these special coefficients, binomial coefficients, that multiply each term, and we denote these binomial coefficients by this notation, a little m up there, then a big C, and then a k down here. So mck, that's the binomial coefficient of the particular term that we're looking at. And then what we have to do is take our first term from the bracket, which is e to the I n pi over a times x, and raise that to the power of m minus k. Okay, then we have to take our second term. We have to be careful because the second term includes that minus sign. The second term is minus e to the minus I n pi over a times x, and that has to be raised to the power k, and then that's with respect to x. Okay, so I just want to simplify this a bit more because there are a couple more things we can do to that. So we still have this 1 over 2i to the m at the front. But then, okay, so we've got the integral of a sum of terms, but the integral of a sum of terms is the same thing as just the sum of the integrals of each individual term, right? So we can actually change the order of the summation and the integration. So I'm going to take this sum from k is 0 up to m, put it in front of the integral. And what else can we do? Actually, this mck is just a number, so we can pull that out the front of the integral as well. And finally, notice that we have a factor of minus 1 to the power of k from this minus sign here, right? Which is also just some number which we're free to therefore take out of the integral. So having taken out all these factors, what are we left with as our actual integral? Well, it's the integral from 0 to a of e to the, well, we can combine our two terms together, right? So there's a common factor of I n pi x over a, right? So let's just write that first. I n pi over a times x, okay? And then, so what do we have? We have an m from this first one, then we have a minus k from this first one, but then we have another minus k from the second one, right? Because there's a k here, but a minus sign there. So what we can do is just write here m minus 2k, and just combine that all into a single exponent. And in fact, what I want to do is just slightly reorder these terms and write this as I pi x over a times n into m minus 2k. Just because n, m, and k, these are all integers, so it's kind of nice to have these all together. Okay, that is integrated with respect to x. And so, what I want to do is look at this integral part of our expression in a bit more detail. So let's take this integral and let's call that j, right? So that is j, and well, that's going to depend on m, n, and k in general. There's 3 integers in there. Okay, so let's have a look at what j actually evaluates to, and we're going to consider 2 possible cases. Okay, so the first possible case is when m minus 2k is non-zero. Okay, so if m minus 2k is not 0, what is j going to be equal to? Well, j is then going to be, well, it's just an exponential, so we can integrate that fairly straightforwardly, actually. We just take what we started with, so e to the I pi x over a times n into m minus 2k, and then we have to divide by the coefficient of x in the exponent, right? So I pi over a times n times m minus 2k. So there we go, just a standard way of integrating an exponential, and that's evaluated at 0 and a, right? And so what does this become? Well, if we plug in x equals a, the x and the a are just going to cancel, right? So we're going to get an e to the I pi n m minus 2k. Then when we plug in x equals 0, we just get e to the 0, which is 1, right? So we subtract off 1, and then that whole thing has to be divided by I pi over a times n times m minus 2k. Now actually, we can simplify this quite nicely. Okay, why is that? Well, it is because this m, right, m itself is even. So we've assumed from the beginning that m is an even number. So m is even, so we take that even number, right, and then we subtract off 2k, but 2k is also an even number because it has a factor of 2, right? So m is even, but 2k is also even simply because it has a factor of 2. Now if we subtract 2 even numbers, we get another even number, and regardless of n, right, n could be even or odd, but if we take any integer and multiply it by an even number, we get another even number. Right, so what this is e to the I pi times some even number, and what is that? Well, it is actually just 1, right? For me, it helps to kind of picture your complex number in kind of modulus argument form, right? So e to the I times something is a complex number with modulus of 1 and a phase or argument given by what you have in the exponent, right? So if you have pi times an even number, it's like you've rotated around 2 pi times or 4 pi times. You've rotated around some whole number of times and just got back to 1, right? So basically what I'm saying is that this first term is just 1, and so you've got 1 minus 1 on the top, which is just 0, right? So if m is not equal to 2k, then the whole thing just becomes 0, which is nice. So how about if it is 0? Well, if m minus 2k is equal to 0, then things are actually going to be different, because j is just going to be, well, this exponential just becomes e to the 0, which is 1, right? So j is just the integral from 0 to a of dx, right, which is simply a. Okay, so in either case, we get different results, but they're both quite simple. And so if we combine these two results together, we can write that in kind of a nice way, because we can say that j is equal to a, right, multiplied by, so now I'm going to use this thing, the Kronecker delta. Okay, so I'm going to write it as delta m comma delta of m and 2k. So basically this delta, if you haven't encountered this before, this is basically, it's either 1 or 0 depending on whether the two things that are in the subscript are equal or not. So if m and 2k are the same, then delta is 1 and we just get a, so that's this case here. If if m and 2k are different, then delta is 0 and the whole thing becomes 0, which is that case there. Right, so there we go. This is what this integral j evaluates to. Right. So let's plug that back in. Let's go back to our expression up here and see what we can do with that. So we know, having evaluated j, we can say that I equals, okay, 1 over 2i to the m. Okay, now this is where we can do a really nice simplification, because we've got this sum over all the k values from 0 to m, but we know that j is going to be 0 for most of them, right? Unless we are at the specific value of k that makes 2k equal to m, j is just going to be 0, and so most of the terms in our sum are just going to be 0. So we can actually get rid of the sum and just say, well, 2k has to be m, right? That's the only way we can get a non-zero contribution from that term. If 2k is m, then k is just m over 2, right? So what we can do is get rid of the sum, and wherever we see a k, we can write m over 2. So let's do that. Our mck becomes mc m over 2. Our minus 1 to the k becomes minus 1 to the m over 2. But then in that case, where m equals 2k, remember our j was just equal to a, right? So that is a. Okay, so looks like we're getting somewhere. Let's see what we can do with that. Well, let's separate out this I and this 2, right? See if we can get rid of that imaginary unit. So let's just have it as 1 over 2 to the m. Okay, then I'm going to take this minus 1 here and write that as I squared, because I is just the square root of minus 1, right? So I can write this as I squared to the power of m over 2, divide that by I to the m, okay? And then we've got our mc m over 2 times a. Okay, and conveniently, right, we've got I squared to the m over 2. We can multiply these two things together and just say that that whole numerator of this fraction is just I to the m, and so that cancels with the imaginary unit on the bottom, right? And so we are left with 1 over 2 to the m times mc m over 2 times a. So we've now actually derived a perfectly valid expression that says what IM evaluates to, right? This thing here. What I want to quickly do at the end is show how this is equivalent to the form I derived in the other video I made about this, which doesn't really look like this. Okay, it ends up being equivalent, and that's what I want to show now. So what I like to do is use the definition of this binomial coefficient. In general, if we have a binomial coefficient, let's say MCR, where R is some number, that can be written in terms of factorials as m factorial over r factorial times m minus r factorial. So in this binomial coefficient here, our r is m over 2. So r is m over 2, but m minus r is m minus m over 2, which is also m over 2. So we can write this as 1 over 2 to the m, okay, times m factorial over, well, m over 2 factorial times m over 2 factorial. Okay, now I would like to use another result which I derived in my previous video. Alright, so not the one about this integral, but I recently made another very short video where I derived a nice identity involving factorials. Okay, and the identity was that basically 2 to the power of m over 2, if m is an even number, 2 to the m over 2 times m over 2 factorial is equal to m double factorial. Okay, so you may want to have a quick look at that video if you want to see where that comes from. Double factorial is kind of like a normal factorial, except when you're multiplying all your numbers together, you step down in steps of 2. Okay, so for example, 6 factorial would be 6 times 4 times 2, rather than 6 times 5 times 4 times 3, all the way down to 1. Okay, so we're going to use that identity, and we're going to do one more thing, right? So our m factorial on the top is actually the same thing as m double factorial, right? So this one covers all of the even numbers from m down to 2, and then we have to multiply that by m minus 1 double factorial. This covers all of the odd numbers from m minus 1 down to 1. Okay, so what I've written here so far is just another way of writing this m factorial. And then we're going to use this identity to rewrite the denominator. Okay, and actually, because 2 to the m is 2 to the m over 2 times 2 to the m over 2, what we've just got on our denominator is this whole thing squared, right? Which is just m factorial squared, or m double factorial times m double factorial, and then there's still this a sitting around, right? Okay, so what we can do is cancel one of the m double factorials and find that this is m minus 1 double factorial over m double factorial times a. Okay, so there you go. Just to kind of really illustrate what that means, for example, if we had, remember m is supposed to be an even number, so if we take m to be 6, what would that mean? Well, I6 would be 5 times 3 times 1, right, divided by 6 times 4 times 2, multiplied by a. So there you go. This has been quite a lot of work. I think it is more sensible to do it the reduction formula way, but I do find it very interesting that we can, just from this definition and a fair amount of algebra, we can arrive at the same conclusion.